All right, we're starting a unit on probability here, and that involves things like cards and coins and dice and all sorts of things that involve odds, things that involve counting things. So we're going to start with a very simple deck of cards. What you see here on page 2 is a row on the top of clubs, a row here of spades, a row here of hearts, and a row here of diamonds. And I know a lot of you are already familiar with a deck of cards, but for those of you that aren't, you will see problems come up like this, so we need to just be real familiar with the terminology. So the first question, how many cards are there in a deck? You could count them yourself. There are 13 in each suit, and there are a total of 4 suits, so that makes a total of 52 cards. How many of each type of card? That means aces, 2s, 3s, and so on up. So there's 4 of each. How many suits are there? Suits are the shapes on the cards, so diamonds, hearts, clubs, and spades. There's 4 of those. If you count straight across the row, there are 13 of each kind. And then you can just write down the names of the suits here. We have clubs, we have spades, we have hearts, and we have diamonds. Okay. The clubs are the ones that are the shamrock shapes, and the spades are the ones that come to a point. All right, so which ones are red? That would be the 2 bottom rows, the hearts and the diamonds. And which ones are black? Those would be the clubs and the spades. Okay, so how many red cards are in the deck? Well, if we have 13 hearts and 13 diamonds, because there's 13 of each, that's a total of 26. That's half the deck. And the same thing with black, there's half the deck there as well. So 26 of each color. Okay, now we go over to the right side here, types of face cards. Face cards are the ones that literally have a face on them. So there's jacks, there's queens, and there's kings. So that's going to be 3 of each, 3 diamonds, 3 hearts, and so on. So that's a total of 12. The names for them, jack, queen, king. How many face cards in a suit? There's 1, 2, 3 per suit. Okay, so that's the term there that you'll see come up, face cards. And numerical cards, cards with numbers. So that would be the ones that don't have an A on them for ace, don't have a J, a Q, or a K. So all the number ones, from 2 to 10. So that's a total of 9. And so that's per suit, right? There's 9 per suit, but there's 4 suits, so a total of 36 numbered cards in the deck. The aces are the ones with the A on them. There are 4 in the deck. And as a note down here for some card games, some games with cards associate values to those cards. Like blackjack and ace can be either a 1 or an 11. Usually an ace is 1, but there are some games where an ace is higher than a king. Some games where it could be both. So it just depends on the rules of the game that you're playing, whether you have a 1 or an 11 in that case. Okay, so on to page 3. We're looking at some coin probability here. So if you flip a coin, as long as it's a fair coin, there's a 1 out of 2 probability that you will get a head, because there's 1 head on the coin out of 2 possible faces. So if you were to flip a coin 10 times, how many would you expect to be heads? Well, if it's going to be half the time that it lands on heads, you would expect 5 flips to come up heads. So you can find a quarter or a nickel or something and flip your coin 10 times. And what you're going to come up with is a number that may or may not be 5. Okay, and the reason for that is this difference between theoretical and experimental probabilities. So theoretical is what should happen. And I'm going to underline the word should, right? What should happen with more repetitions based on the math. The experimental is what does actually happen after you conduct the experiment. What does actually happen. So we would expect theoretically for it to come up 5 times on heads, but in reality, after doing an experiment, you might have gotten 3 or 4 or 7 or whatever. If you were to perform this 100 times, what would the outcome be different? Well, we could flip a coin 100 times, but what the math of it says is that as the sample size increases, and sample size means the amount of times that you do the thing, so as the sample size increases, the experimental result moves closer to the theoretical result. So if you were to flip it hundreds of times, we would expect it to get closer and closer to half of the flips that land on heads. But if we only do it 5 times or 10 times, then we are having a lot of variation there. Okay, so what we would expect in theory is for the number of heads in 100 coin tosses to be 50 and the number of tails in the coin tosses to be 50, and therefore 50% for each. We could run a simulator. We're not going to do that right now, but we could run a simulator that shows all those different probabilities. As the numbers get bigger, as the number of trials get bigger, we would expect it to come closer and closer to that expected probability. All right, so going on further here. On page 4. So now we're looking at dice. And when you roll 2 dice, every die is a cube, and on each cube there are 6 faces. And they're numbered from 1 to 6. Each face would have a little pip in it that tells you what the face is worth. So you could have a 1, you could have a 2, you could have 3, up to 6. So when you roll a die, there's a number on it. Okay, so one of the most common sample spaces is the rolling of 2 dice. Use the table to list all the elements. So if you roll a 1 and a 1, you get a 1, 1. If you roll a 1 and a 2, you get a 1, 2. 1 and a 3, you get a 1, 3. We could keep filling that in. When you then make the sample space the sum of those 2 dice, what you would be doing is adding up the 2 dice on that you've rolled. So if you roll a 1 and a 1, you get 2. Roll a 1 and a 3, you get 3. If you roll a 1 and a 3, you get 4. A 2 and a 2, you get 4. A 3 and a 1, you get 4. So there's 3 ways to roll a total of 4. There are 4 ways to roll a total of 5. You could do 1 and 4, 2 and 3, 3 and 2, 4 and 1. Okay, and if you keep on filling in this table, you're going to see there are more ways to get the numbers as we go. All of these are 7s, but then it's going to come back, right? So if I roll a 6 and a 2, I get 8. If I roll a 5 and a 3, I get 8. And I'm getting 8 for all of these sums. The number of 8s is the same as the number of 6s. If I do the 9s, 6 plus 3, 5 plus 4, 4 plus 5, 3 plus 6, the number of 9s is equal to the number of 5s. So it's diverging from the middle here. The 7s, there were 6 ways to get them. And then as we go below and above 7, there are fewer ways to do it until we get back up. I'm going to just do the 10s, there are 3 of them. Do the 11s, there's 2 of them, and there's only 1 way to get 12 if you roll a 6 and a 6. So on the extremes, there's only 1 way to get a 2 and only 1 way to get a 12. Then we get more as we go closer to the middle. All right, so that's a pretty common concept of dice. If you were to look across the entire grid here, I filled in 36 numbers. That's because there are 36 ways to roll the dice, and a lot of them are the same result. But there are 36 ways those dice could come up, because the ones in this column are considered a different die, a different cube that I'm physically rolling than the ones in this row. So there's die 1 and die 2. There's all 36 ways that those dice could come up. Okay, so if we were to make a graph for this, it would make a bar graph that would go up and up and up and gets to 7, and then it comes back down and down and down and down at 12. All right, so I'm going to skip past that and go down to the bottom here, the sample size for rolling 2 dice. We just said there are 36 ways for it to come up if you roll 2 dice. There's 6 for the first die, 6 for the second die, so 6 times 6 is 36. The sum that was most likely, you look back here at this chart, there were 6 ways to get a 7. Nothing else had that many occurrences, so the 7 is the most likely. It occurs 6 times. Okay, the probability of getting that sum would be the 6 times it happens out of the 36 different combos that could come up. And we reduce that fraction and we get 1/6. So the probability would be listed as 1/6 of the time we would expect to roll a total of 7. The least likely to be rolled were the extremes, the 2 and the 12. Oops, not 16, the 2 and the 12. And the probability of getting the least likely sum, each of them only comes up once out of a total of 36 possibilities on the grid. Okay, so that's the basics for rolling dice problems. Okay, and that should do us. I know there's a page 5 in this intro section too. I mean, I'll quick look at that, but that's if you were rolling different kinds of dice, like a D4, which is this triangle shape. Well, then you could get 1 + 1, 2 + 2, 3 + 3, 4 + 4. So there's, 4, yeah. So we could get 3s. If you do 3 + 1, you get 4. 2 + 2 is 4. 3 + 1 is 4. You can get 5s, but you can't get 6s. Right? So then this, if you do 4 + 2, you get a 6. 3 + 3, you get a 6. Here's a 6, 7s, and 8s. But we can't go above because there's no 5s and 6s. So that's what changes there. The sample space is 16 total possibilities. All right, so we'll leave it there. You've got other probability problems to work on today. Just wanted to give you an introduction to that concept.